very much the theme of how we sort of deal with this intro course is that this is a very gentle introduction to engineering, one to really give you a feel and the flavor for what engineering actually feels like. I think to some extent on Tuesday you sort of got a good impression of sort of how iterative engineering is. You try, sort of come up with design, you test it, you realize something is needs to be fixed or mended, needs to go back, and you will repeat that process really many, many times. And it's often very hard to tell yourself and figure out when do I say this is good enough, that I have to move on, that I can't work on this one project forever. You also probably got a good instinct that a decent bit of engineering is about calculations. It's something that we don't want to burden you with too much now. There's time later on to sort of dive into that. Even later on in this course, we'll deal more with the quantitative side of engineering, and of course, equipping ourselves with tools so that we're not doing as much pen and paper math. We have a way to automate a lot of difficult calculations for ourselves. But still, we're trying to get a feel, and particularly, we're trying to improve upon what we probably experienced on Tuesday. This idea of how do you sort of figure out, one, how to balance different priorities. In making our boats, we had to prioritize the difference between a particular design versus a volume. How large can we make the boat versus how thick can we make the walls, or how rigid can we make the structure? In many cases, we always have to have trade-offs between different things that we'd like to do. And how do we rationally decide on those trade-offs? How do you all agree on what we're going to be prioritizing? And really, for that, engineers, as well as other people within business and social scientists and things like that, anchor on this idea of key performance indicators, KPIs, and other ways to sort of set win conditions for ourselves. So throughout the semester, we're going to be going through, sort of walking through and teaching ourselves and practicing this engineering design process. How do we start with a problem and eventually come up with a solution? And next week, we'll begin to actually dive in and begin to pick the final project we'll work on throughout the rest of the semester to really put into practice a lot of the things that we'll learn sort of more abstractly in sort of these more test cases. Ultimately, everything has to begin with this task of identifying the problem and making sure we have a problem that is worth solving, that we're willing to engage with for a while, and that we understand and are able to model or predict why this problem exists so we can ultimately try to target some sort of root cause, the root reason why this problem exists. From there, we sort of move into the more creative side of stuff, which we practice a lot in this lab portion of this course, really just trying to brainstorm and use this creative engineering to come up with different solutions, which might be very, very practical, straightforward, might be quite wacky and impractical, but still important to have that creative space. And most importantly, to try to build and prototype and to turn those into something that you can actually test. Engineers get into a lot of arguments about theoretically trying to predict what will happen, and we all have different estimates of how things will behave, but ultimately it all falls down to how the actual thing behaves in the real world, and we really have to either put up or shut up with a lot of our ideas. We test and iterate and go through this whole process as many times to try to refine as much as we can, and ultimately we have to be able to communicate these ideas out to someone else. We practice, of course, first today, trying to communicate our ideas as succinctly and accurately to our fellow engineers who are also versed in our art, who are also very technically minded and kind of understand where we're coming from. But eventually, towards the very end of this course, we'll worry about how to present our ideas out to the general public, how to make what we, very nerdy, detailed, technical-oriented people, understand on a certain level, but try to relate that to the average person who will be using our solutions, who need to understand what it is that we've done, why it works, why they should be excited about it. We sort of break this down into both analysis as well as modeling and optimization, sort of the design aspect of engineering. And of course, we'll go through this both in these sort of activities, but we'll do it again in our final project. Now, ultimately, this process, this transition from sort of thinking about things and coming up with potentials and trying to narrow down on a single solution that we try to optimize as much as we can, requires us to be able to judge which solutions are better. which potential designs solve our problem better in whatever way that we may call that. Typically, we want to have something that is quantitative so we can compare numbers, which are a lot more objective than our sort of feelings and ratings about things. And we want it to be metricized so that if we evaluate how one potential solution behaves, another person judging that same solution should come up with the same score. We should all be working under the same definition of how we rank things. For that, we often use this idea of a key performance indicator, which is a way for us to sort of create essentially judging rules for how we judge whether a solution solves a particular problem, particularly for when there are many different problems to be solved and many different criteria that indicate whether the problem is solved. We try to establish those before we begin to evaluate anything. So we create the rules of the competition before we start the competition, so it's as fair as possible and as objective as possible. And of course, there are better and worse ways to set out these types of rules for evaluating different solutions. So this idea of a KPI is not unique to engineering. You'll find it within business and economics, other parts of science, particularly within sort of that transition from science to business. A lot of the biotech found here in the Boston area uses this idea to try to balance not just technical criteria, how well does this solution perform, as well as incorporating business things. How desirable is this to a customer? How expensive is it to make, so on and so forth. We try to make sure that they're numerical and quantitative. We try to assign a number, even if it's somewhat of a semi-quantitative thing. The reason why we often will rate movies or TV shows, as we were talking about previously, with a 1 out of 10 rating is that it gives us some way to compare apples to apples rather than compare I like this versus I didn't like this, or I like this a lot, so on and so forth. Usually we try to make these KPIs based off of what the end customer is going to use to evaluate. We, of course, have our definition of what makes a good solution, but ultimately we are not going to be using, adopting, and paying for the solution. So we need to make sure that our definition of success aligns with our customer or client or whoever else. In many cases, we sort of set several KPIs at a sort of minimum level, which a minimum level we expect to meet, sort of where we would like to be in expectation, and then sort of a stretch or reach goal. In very much a similar manner, your grade for your courses is a type of KPI. We have a syllabus that tells you the different ways that you'll be evaluated. Each assignment is worth so many points. Each assignment versus a test versus a lab is worth different portions of your grade. And we lay out the rules of how we evaluate at the beginning of the course. But we also set several different levels of meeting those KPIs. Whether you get a C or a B or A reflect all different degrees to which you satisfy this performance indicator. We try to do it at the beginning because we're always very tempted to sort of bend the rules as we go along to favor a solution that we like more than others for whatever reason, but we try to do it as objectively as possible so that we all are working towards the same goal. Mostly our KPIs within engineering focus on how do we optimize and sort of figure out what's a acceptable cost or as well as price for the thing that we create. How much resources does it require? So how much time does it take to build this particular bridge design? How much space does it take? How many people does it take to construct? All sort of are things we often talk about. And then, of course, very much more technical things, talking about how much material maybe our bridge might require, so on and so forth. Finally, the last one, which is always very important, particularly for engineering, is some measurement of perception of the quality of the design, how nice our design or solution might be. As we talked about previously in the passing weeks, particularly looking at the case of McDonald's, of when they first rolled out their fancy new ultra-fast hamburger service system, regardless of how cheap we can make hamburgers, how quickly we can make them, how efficiently we can make our hamburgers, if the public doesn't know what to do with a walk-up fast food counter because they're used to drive-ins where someone will come to your car, none of our other KPIs matter if the perception of what it is doesn't align with our customers, with the people. So we often have to account for the unknown variable of the customer or the average person. So how do you make one of these good KPIs to make sure that we all understand the same goal and that we have very specific ideas of what we're aiming towards? An acronym that you'll come across in engineering as well as other fields is this SMART acronym, which sort of gives categories of how we define a good KPI, a good goal that tells us everything we need to know. SMART stands for, there's different variations, but at least for engineering as I use it, SMART stands for specific, meaning that our KPI or goal must be very, very specific about what we're aiming for. It should not really be open to interpretation. Everybody should have the same definition of what we're trying to improve. Specificity is good. If you were to run a pizza shop and say we want to increase efficiency, that is a way to specify a KPI, a goal, but efficiency means a lot of different things to different people. A better KPI or better criterion would be to say we want to increase the number of pizzas produced per person per hour. Again, everybody should have the same definition, and being specific is helpful. It should be something we can measure, something that is not something that is either quantifiable by some sort of number of pizzas produced per person per hour, or something we can measure with specific units. But we can utilize a more qualitative rating like a perception. Engineers and other product marketers will often use a survey system in which people rate from 1 to 5, which still gives us a measurable thing we can use to judge how people feel about a particular solution. It should be actionable, of course. We set these goals, and we should set them so that we are expected to achieve them. They should be also something that we ourselves can control. If you were a pizza shop trying to optimize and create KPI goals for yourself, you could control and find ways to increase the number of pizzas produced per hour. You as an individual pizza shop probably couldn't find a way to make tomatoes cheaper or to prevent the drought from ruining all the wheat crop in Ukraine, so then the flour is more expensive. So we pick things that we ourselves as problem solvers can deal with, something that we can do proactively, something not out of our control. It should be relevant, of course. These should be related to our problem. Ultimately, the relevancy is usually defined by the end user. Again, we have our definition of how things should work and how to solve a problem, but ultimately, the only person whose opinion really matters at the end of the day is the customer, the client, whoever's problem we are solving. And finally, timely. This is the one that engineers struggle the most with. Engineers have to work within timelines and goals and budgets, and it's going to always be a problem if you just set a start point of a project and an end point of a project. You're going to be tempted to leave everything up in the air until the very, very last second. One reason why in school, as you run through your exams and tests, we have due dates throughout the semester to turn in assignments. In theory, we could say there's one due date at the very end of the semester for every piece of homework, every test you could take, but most people probably won't be able to space it out accordingly and will rush through and try to complete everything at the very, very end to varying levels of degree. So we usually try to set timely goals to say this goal must be met within the first day or something in order to make sure that we're on track and on pace to probably satisfy several KPIs. So this sort of is a rule of thumb, a guide. This does vary depending on the type of problem you're working on the KPI, but we'll take a look at some examples just to get an idea of how we think about it. So let's take, for example, the cafe down in the main lobby of this building, the Bunker Hill Cafe, which is a business that has problems, and very much in some instances a engineering set of problems. They have materials flow in, they have food and products flow in, they have to sell it, they have to make sure that their cost and labor and technology and all those things balance out on a very quantitative basis at the end of the day. And like any sort of business, they have their priorities, which could be improved in a rational, well thought out manner. And if you were to ask this cafe, they probably would say that the two very general categories they would care about would be financial stability of this cafe. This is a thing run by sponsored and run by the college, so they probably aren't looking to make huge profit and sort of become millionaires, but they want to be financially stable. They want to make sure that they don't run out of money, that they don't have to scramble if they run out of workers, things like that. And of course, by serving the college, they care about student satisfaction. They want people to come to this cafe to use it. They also want them to be happy with their service. But these two goals, or sort of these two priorities, aren't good KPIs. They're very ambiguous. How do you do things to improve the financial stability? How do you do things to improve student satisfaction? Different people have different solutions and different answers. A better engineering approach would break these very general categories into more specific, more smart KPIs that might say the financial stability, understanding and modeling that problem really comes from how much do all of your expenditures cost. So how much is your salary or wages and labor? How much are the food products you buy? The equipment to house all of your beverages and things like that. You may sort of look at what the monthly revenue is, sort of how much are they selling, student satisfaction as a survey score, and other ways to judge student satisfaction. Again, trying to break these down to more specific terms. How these would look as smart KPIs for an engineering approach would be to say, we want to move from a bad, not specific, not measurable KPI like how much money do we make, which is a fine place to start, but we must move on from there. And we might sort of break that down into a better KPI, a better thing we are evaluating how this business, how this operation is doing. We may want to say that we're going to try to track and optimize for the monthly gross margin from pre-packaged foods. Again, we're trying to be as specific as possible. We try to be specific, so we'll try to break it down. All the things that this cafe might sell, we'll sort of pick a single category so we can track the different things that this cafe might sell. So we try to be specific as possible to give us more insight to what aspects of this business may be in need of most improvement. We want it to be measurable, and here we will quantify how much money you make. Many ways to quantify how much money a business makes as a gross margin, which is basically how much does it cost for them to buy all their stuff and pay their employees, minus how much they will earn as revenue from selling all those things, and of course normalized or divided by revenue. So some sort of percentage that tells how much money on top of their costs are they making or are they getting back in return. So we want something we can measure and calculate, and everybody would calculate the same way. We make it actionable. We sort of break these goals down to things that we can affect. This business can change their operating costs by figuring out who they buy their food from, how much they pay their employees maybe, which we probably don't want to cut back too much. And of course, revenue, something you can do by increasing marketing or offering sales and things like that. We want to be relevant. Of course, gross margin is a term that not just engineers will understand, but people operating a business will understand. So we can kind of make sure that they would agree that this is a good goal to aim for. We use terms that they understand as well as we understand. And then finally, we want to make sure that this is a monthly thing. We want it to be a timely measure and sort of set timely goals. We could say that, we just want it to make more money. But depending on whether you track that on a day-by-day basis, a week-by-week, month-by-month, year-by-year, gives you different insight, gives you different information. And ultimately, if you only track things year by year, you only see very slow changes once every couple of years. So we try to break down these kind of goals and be as specific as possible, as quantitative and as timely as possible. By looking at sort of setting this KPI, it sort of tells us what do we need to value, what do we need to optimize for this engineering type problem. We would want to see how our current prepackaged foods are performing in terms of their sales. We want to evaluate all of our operating costs versus our revenue. And we want to sort of use that as a basis to figure out what's a reasonable goal for ourselves to set for improvement. Obviously, the business would like to make as much money, as much gross margin as possible. What's a reasonable goal for ourselves? In many cases, it starts by having understanding of where you currently begin and making some estimates from there. Again, we try to do this before we set out on the process because you're always tempted to change the rules as we go on. But we try to calculate as much as we can and try to figure out where we begin, just so one, we can set reasonable goals for ourselves. So we might be able to calculate and figure out that based on the current operation of the cafe downstairs, that they technically lose a little bit of money on their pre-packaged foods. Maybe they would consider it as so-called a loss leader. But where they currently operate, they gain or they earn 10% less than they pay to sell that pre-packaged food, which may be okay for them. From that, we can now set a reasonable goal for ourselves. A reasonable goal may be to say that rather than operating at a loss, at minimum we would expect this operation to break even, a very reasonable standard to expect. From there, we could sort of set smaller increments, things again that we do in consultation with our customers to figure out, is it reasonable to change your operating cost of revenue by 5%, by 15%, potentially. They would probably tell us it's probably not reasonable to expect to change it by 100%, 150%. We can set reasonable goals based off our understanding of where we currently begin with this KPI. From there, of course, we do our brainstorm, we begin to ideate and come up with different solutions, but now trying to evaluate them through this lens of what would affect, for example, this gross margin. Because this gross margin comes from two things, and we've modeled how we calculate the gross margin as being a function of the cost of all our stuff versus the revenue, how much money we earn from it. We could come up with solutions that either lower costs or increase revenue, quite sensibly and straightforward, giving us a little bit of a better way to take whatever creative idea we might have for this cafe, but try to identify the ones that would either lower costs or increase revenue. Something like painting the cafe a different color probably doesn't lower cost, may or may not have an impact on revenue. So we begin to sort out our ideas from there. One thing that I would caution, or not caution, I would suggest to keep in mind is that as we move through both this example, but as you sort of begin to tackle your own final projects for this course, engineers often have to sort of decide between different types of solutions. And one way we can break apart the two different categories of solution is between proposing a change in a process or a new product that might solve our problem. And neither are necessarily better or worse than the other. They have different attributes to them. Process might be something, of course, changing how we do things, or the way that we might organize where our chips are located within this cafe, versus a product solution would be requiring something new, physical, tangible, maybe a different type of chips, maybe a different machine that sells French fries instead of chips. So for this singular KPI of trying to increase the gross profit of this cafe, we might be able to propose both a process solution, something like finding a different bulk vendor who will sell us the chips and sandwiches at a lower wholesale price, so lowering our cost. But we may also include something that tries to deal with the labor aspect of our costs. So we're working on better scheduling to make sure not we're having overstaffing during low hours. And of course, engineers often love product solutions, so we get to design a fancy new tool. Maybe something that could help lower cost, lower labor would be to have automated checkout machines in the cafe, more vending machine type things, maybe fancy new things that will attract more customers because they're more attractive, like one of these Coca-Cola Freestyle machines that sort of let you mix and match sodas. So different ways that we could all solve this increasing the gross profit, some process, some products, both trying to target, again, either the cost or the revenue aspect of this particular criterion. From there, we try to measure and try to test and try to ultimately verify which of these potential solutions are more likely to have a bigger effect. We use these KPIs to make sure that we're judging them equally and fairly as possible. And in many cases, it requires a little bit of guesswork, a little bit of testing ourselves. And in many cases, the ultimate decision comes down to not just one KPI, many ways to increase gross profit for a organization, but that's probably not the only thing that our cafe will care about. And of course, any solution we have will not only affect one KPI, it'll affect a lot of different things. So how do we balance different priorities, different criteria for a particular solution? For that, engineers will often use what we call a pew chart. A pew chart is a way for us to, in a very semi-quantitative way, to balance different priorities. For our cafe, we might say that what they care about is the gross profit that they will earn on a monthly basis. They may also care about any new equipment costs. Equipment cost is sort of not usually factored into gross profit since you sort of pay out once to buy a machine, and you have to have a lot of money upfront or take out a loan. So it's a different category, different KPI. They, of course, care about student satisfaction, and usually we estimate some level of risk. Any new idea is untested really at the true scale. And so we have to estimate how much risk or unknown factors might there be. Uh, these four KPIs all matter to our cafe, but maybe they don't matter as much. Maybe they don't all matter equally as much. We might say that something like the gross profit is the most important thing for this cafe, versus equipment costs and student satisfaction, still important, but less important. And then something like risk is something they recognize but don't care as much as the other factors. In order to evaluate each of our different potential solutions, we have to figure out how to balance these things. And we can either do it quantitatively, or we could sort of give it sort of a 1 to 5 score on how these would satisfy these different KPIs. We will look at something like a relatively simple solution of finding a cheaper place to buy the chips and sandwiches and prepackaged foods. And we would rank it according to how that seems to perform. Obviously, it will probably have a reasonable effect on low or increasing our gross profit by lowering costs. It's very favorable, 5 out of 5 for equipment costs because you don't have to buy any new equipment to find a different chip supplier, so on and so forth. Compare that to something like a buying a automation, sort of a self-checkout new gadget for the cafe. Obviously, it's going to decrease our labor, so increase our gross profit, so very favorable, but very expensive. 1 out of 5 scoring for this particular category, and also very, very risky, since even big places like CVS and Target struggle with self-checkout for a lot of reasons. And so to combine all these different factors and figure out what is the most promising solution versus one that we may look at in a far different time, we effectively take each of these scores multiplied by this weighting factor. So the higher the weight, the more important we view it as. And then we sort of sum up and tally up the net weighted score for each of these solutions. This is sort of what we think of as a pew chart. And from this, we can say, based off of this scorecard, that some solutions, like simply just getting new products, as a net effect, doesn't really have as much impact we would predict as something relatively simple like finding a cheaper supplier for chips. Other solutions might fall somewhere in the middle, but we have some way now to all agree on some sort of way to evaluate which one maybe we'll evaluate, look at, test first. If that one doesn't work, which one do we move from there based on how promising it might seem? And so this is one way, and there's many different ways to do this. We could always sort of substitute in a measured property, like what the actual calculated gross profit should be, 10% versus 50% versus minus 10%. But we can also do this semi-quantitatively just to kind of get a relative rating for it. Yes?
There in automation, the risk is 4, right?
Yeah.
So does it mean, is it safe or not?
This would be that it was unfavorable for risk. So it'd be more risky because maybe new technology, maybe the machine doesn't work, maybe people don't know how to use it, maybe people are more likely to steal. And so whether the score is high or low, sort of you have to set it up and know how to interpret it. This is one example. There's different ways you can kind of create a combined score. And of course it changes if you as an engineering team decide, for a business that has to serve the student populace, and if they go out of business, it's a huge problem for the college. Risk actually is more important. And the fact that this is very risky makes it a lot less favorable, a lot less desirable. So you may change this way to move it up in sort of the list of priorities. And so this is where a lot of engineers will spend time debating, arguing, calculating, trying to determine what do we all agree on the relative weight or importance of these different goals. Evaluating how they meet those goals can also be done. Again, quantitatively, we can calculate things, but we can also use our judgment and interpretation. But we always try to get such that we can have a final single score to rank these essentially in order of most promising, most desirable to least. But there's many different ways we might pursue this. Another way that we might begin to look at how do we rank different KPIs, how do we rank different solutions, would be to see what actual effect do each of these KPIs have on our final desired outcome, which is sort of financial stability for this cafe. One way we can do this is by creating a tornado chart, which tries to calculate, very much a numerical basis, what is the effect of any particular parameter on our final desired deliverable, trying to identify which is the most sensitive KPI to what we're after. So let me give you sort of the example. So there's many different things you might evaluate and characterize about this cafe. You might try to rank or measure how many customers do they get per hour, how much are they charging for a sandwich, how much are they paying their workers, so on and so forth. All of which have some sort of effect on the gross margin. Previously, we looked at very simply at cost versus revenue, but of course those can be broken down into more specific categories. Now, there's many different ways we might lower costs and increase revenue. We might try to attract more customers to increase revenue. We might raise the price of the sandwich to increase revenue. We might try to lower salaries to decrease costs, so on and so forth. Numerically, they all have different effects on our gross margin, things we can calculate. And something we can do, this tornado chart tries to show us if we were to have a certain change on each of these parameters. Let's say we're to increase the number of customers per hour by 20%, or decrease the number by 20%, or we were to increase the sandwich price by 20%, decrease by 20%, what effect does it have on our final price? Which is going to be the most impactful versus less impactful or least impactful? From things we can calculate, and in 2 weeks, we'll have a good session with Excel and other spreadsheet programs to sort of generate this type of more complex calculations. We can see that not every way we might increase or decrease costs, increase or decrease revenue, has the same effect. How many customers we can bring in per hour, it has the biggest effect. The largest change on our gross margin based off of a relatively small change in the number of customers. Things that have less impact is the cost of the prepackaged snacks, the cost of the drinks, how many snacks a particular customer might buy. Things which do still affect our gross margin, but doesn't have as big of a quantitative effect. And we should end up with some sort of this type of tornado shape, showing things that have a big effect at the top, things that don't really matter as much at the bottom. This again helps us define and narrow down things that might be important versus less important in this final KPI. So we can use these ideas to try to evaluate as quantitatively as we can our different solutions. We can say, if we were to really not do anything, we would sort of have a negative gross margin. As we change our wholesale pricing, we increase automation, we bring in new products. What does a small change versus a large change have an effect on this gross margin? Again, trying to go from a relatively generic guess of rating it from 1 to 5 to something that's a little more quantitative, something a little more numerical. We'll work through these types of calculations in a couple of weeks, but sort of setting out the idea that we can begin to evaluate how each of these potential solutions perform, both on a sort of judgment qualitative basis, but we can calculate these things, again, depending on how good our model, how good our sort of equation for any of these KPIs might be. So these things are sort of hard to talk about in abstraction without sort of concrete examples. And even this cafe example is not really a good crunchy engineering one we can sort of get our hands on. And so to try to give ourselves some experience with setting goals and KPIs for ourselves and then trying to follow them, we're going to build some Rube Goldberg machines. So a Rube Goldberg machine, we haven't seen one before, is really at the end of the day a very complicated factory that consists of several automated parts. It sort of is like a chain reaction of dominoes, things that will run on themselves without human interaction to do something. In many cases, it is moving a ball or a marble from one part of the machine to the other. They're quite silly in that they don't really have a function and a purpose. They don't really do many things. And in many cases, they're not the most efficient way to do something like move a ball from one end to the other. But they still are good tools for us, one, to use our creativity, sort of have a little fun, but also practice dealing with very complicated systems, as you might have in a real manufacturing factory, of which you have to balance a lot of different factors to optimize and improve how this machine works. Some physical actual examples we see here, again, often assembled from relatively simple parts, employing different types of mechanisms, devices to move, to do something very simple, like moving, this case, a marble from the left to the right, but all sort of employing different mechanisms, different mechanical bits that really test your creativity as an engineer. Another example, again, very simple parts, very simple components, quite often using little devices that may be helpful in future engineering designs to solve different challenges. Here, an abundant use of magnets to convey and create forces, all of which should serve as some inspiration for our activity for today. We're going to, or you will, build me the slowest gumball factory. I have several gumballs for you, and our job today is to make 10 gumballs from these manifolds, so these sort of steel bar structures on the end of the lab benches, into this bucket, which will be placed right there in the center between those two benches. We will divide ourselves into two teams, and we will build two sets of Rube Goldberg gumball factories. For that, we'll start at the top of those steel poles, and then we'll go down to the floor there. So we have the force of gravity really doing most of the work for us. If there's other things that you figure out how to employ, you're welcome to do that. The job of this particular factory is to convey gumballs as slowly as possible from start to finish, as well as, of course, accurately and reliably as possible. If the gumball falls off or it gets stuck along the way, doesn't count as being a slow travel. So we're going to try to optimize towards these two very generic goals, not very good SMART goals as they are, not very good KPIs, requiring some more specifics on how to actually achieve these slow gumball factory things. Primarily, I have a bunch of paper goods, so cardboard, paper. I can scrounge up some other things, and you're also welcome to use any other materials that you have on your person that you can find that's not terribly destructive, both here within this lab. In previous semesters, people have just sort of run rampant across campus or trying to steal anything that isn't nailed down. Try not to be destructive or terribly obtrusive, because we do get complaints if people take liberties, but you're welcome to really use anything to construct your Rube Goldberg machine. The only specifics of how it is built is that your factory, your Rube Goldberg machine, must have 3 separate sections, 3 different things, and they must be not touching each other. So there must be some sort of air gap between for the gumball to sort of drop or fall from one to the other. Otherwise, you're welcome to incorporate more mechanics, more different functions and things like that, again, to try to slow down the travel of this gumball just as much as possible. Your job and your task, and really where you need to flex your engineering skills, is to try to, of course, plan and work together as a team. We have finite time for this, of course. And you need to sort of create your own criteria for what you're building, how you're optimizing for it. This game or this activity is one very much of trade-offs. You want these gumballs to move as slow as possible without stopping or getting stuck. And how do you do that? You could potentially make one really, really slow section. The other two could be pretty fast, and so you could balance the issue of having something that's slow but still reliably gets to the end by prioritizing one really slow and two very accurate sections. You could try to make it very, very complicated with a lot of different parts, but of course, every time you add something new to your design, it complicates it. It's another place your thing might fail. As we sort of saw with some of our boats and our parachutes, the more complicated we made it, sometimes it got better, but in many cases, it just created another way for it to misbehave. So how do you balance complexity versus efficiency? How do you balance having something very, very slow versus something that's very reliably gets every gumball to the end point? And you're welcome to sort of include as much creativity as you have within you. I do look favorably upon that. Here's a twist. You as a team of 3 will have an hour to work on your gumball factory. During that time, you should build as much as you can, but particularly make sure you have a good idea of the design you're aiming for and the KPIs, how your factory is going to be optimized to have the slowest set of gumballs as possible. At the end of the hour, each team is going to switch places with the other team, and you'll work on the other teams, and you'll finish the other team's Rube Goldberg gumball factory. You may not actively help and communicate with the other team as they're finishing up your factory. All that they're allowed to go off, of course, is their own engineering intuition, but any sort of written or drawn designs of what you're aiming for, as well as your KPIs of, are you optimizing for one very slow section, 2 very reliable ones? Are you trying to make it as complex as possible? However you decide to meet this particular brief and this particular challenge. Since everybody's sort of working on all machines, your score and your grade for this activity will be the same one that everyone else gets. For each of our machines, for each of our Rube Goldberg factories, we'll run 10 gumballs through them. And we'll time how long it takes each gumball to go through your machine from start to finish. Your score of 10 points is going to be how many of the 20 gumballs, 2 times 10, their total travel time divided by this scaling factor of 50. I believe if you do the math, in order to get the full 10 out of 10 points, each gumball has to have an average travel time of about 25 seconds. So you have to slow it down a decent amount. One thing, of course, the reliability comes in is that if a gumball gets stuck along the way or falls off your track or somehow doesn't get to its intended target, that, of course, gets a travel time of 0. So you have to balance whether you want reliable gumballs that always get to their end but a little faster, or very, very slow ones that may sometimes get stuck, may sometimes not reach their final destination. So that is our task for today. We'll do an hour and then switch, and then 1 more hour, and then we will run and evaluate this at the end. Yes?
Can we choose whether we want to roll 1 gumball at a time or 2 at a time? Or
so as depending on how you do it, I'm open to other suggestions, but because we want to time each gumball on its own, and we want to see sort of the failure rate, how often a gumball gets stuck, the plan will be to do it 1 at a time. But if you're welcome to also incorporate, it doesn't have to be the same gumball that starts and ends in that process. You can have sort of a chain reaction domino type thing in case that's part of your designs. But from the time the gumball is released up there to the gumball lands in the bucket down there is a time we will time for one run, and we'll do that 10 times per machine. All right? So I am willing to let you figure out how to divide yourselves into your two teams, unless we would like to do it randomly.
I think
Let's do it randomly. We'll do it by picking gumballs. So you will have the gumball, of course, to play with and evaluate. But so as not to get our hands terribly dirty up front, we'll use these plastic model atoms that are not sticky to figure out how. And we'll divide our teams. Alright, without looking, twirl it around, pick a ball. Yeah. Alright. Twirl around, pick a ball. All right. You don't get a choice. You know, what you have when you sit in the back. All right. So let's say green versus red. So one machine will start here. You may take as much of the room as you need. You may send it anywhere you would like. So this is your starting point. This is the starting point for the other machine. And your target, however you choose to get there, will be this bucket, right there. I have an abundant amount of soon-to-be recycled paper to construct your different ramps and funnels and pulleys and things out of. Masking tape, scissors, cardboard. I can find other things for you if you have other things that you would like. You're welcome to incorporate anything you find or have. Everyone grab as many gumballs to test it out as possible. Important to note, and again, why reliability is important, gumballs are not perfectly spherical. They're mostly round, but they're not perfect spheres, creating another thing to factor into your design. All right. We will go until 11. At 11 a.m., we will switch and you will work on the other machine. At 12, we will test them and see where we stand. Got it? All right. Off you go.